Today we're going to be talking about optimization with linear programming. What linear programming is a method of finding the maximum value of a function that satisfies a set of inequalities. And you're going to have the inequalities, which we call constraints, the feasible region, the region that we graph. So when we graph our constraints, that's going to be our feasible region, and then our objective function, the function that maximizes or minimizes the values from our feasible region. And an example of this, okay, where we're bounded, where we have vertices and each one of our inequalities bounds an area, okay, and we're always going to have a maximum or minimum at one of the vertices. So we're going to find these intersection points, and we're going to be plugging that into our objective function. Now, when we are unbounded, okay, when I have an area that I don't have a line here that bounds that area, we're not going to have a maximum or a minimum. There's going to be one of them that's going to be restricted. So let's do an example of this so you guys can see what's going on here. So we're graphing the following system of inequalities, naming the coordinates of the vertices, and then we're finding the maximum and minimum according to our objective function. So that's what our objective function looks like. So we graph our inequalities. X equals 5. And y equals 4. Now graphing this line, and you guys can put them in slope-intercept, and that's fine, but I'm not going to lie to you guys. Linear programming is made a lot easier if you graph things by intercepts. So if you make x 0, y would be 2, make y 0, x would be 2. And we graph our lines. And make sure that you guys are using straight edges. I don't have a straight edge on my smartboard. But now when we're looking at graphing these, x is less than 5, y is less than 4, and if you look at this, y is going to be greater than or equal to 2 minus x, so I'm going to shade this triangle in here. So we need to find our vertices. One of them, that one is super easy to find. It's our x equals 5 line, this is our y equals 4 line. So x would be equal to 5, y would be equal to 4. Okay, and then we're going to be testing these in our function f of x, y is equal to 3x minus 2y, and then finally figuring out who's the maximum or minimum. Now we need to find the other points of intersection. This point of intersection is the intersection of y equals 4 and this line. So if you plug 4 in there for y, because we know the y coordinate has to be 4. Okay, I know the y coordinate has to be 4, and I solve for x, we get a negative 2. Now notice how, yes, if you've graphed this correctly, the line, it looks like it's where the two lines intersect. Okay, but understanding that, plugging in these values into the other equation is going to help you guys find the intersection points. Here for this point down here, x equals 5. So if I make x equal 5 there, and then I solve in the other equation, I subtract the 5 over, we get a negative 3. And yeah, that's where it looks like the intersection points are, so that makes our life a little bit easier. So now it's just a matter of plugging in your x and y points. Okay, when I plug in that point, we get 7. Now when I plug in negative 2, we get negative 14. And then when I plug in, oh, this should be a 3 here, guys. 3, and then I plug in 5, minus 2 times a negative 3. We get a 21. So here is where our max value is going to be, and this is where our min value is going to be. Eventually, we're going to be applying this to word problems. So that's what we're really doing here, is we're going to eventually be applying this to word problems. Let's do another example, an example where we're unbounded. Okay, so this first line here. I'm going to copy that line down here. Now, if you find your intercepts, again, I think that's the easiest thing to do. So if you make x 0, y would be a positive 1. If you make y 0, x would be a negative 2. So plot those points. 0, 1, negative 2, 0. It looks like our slope is 1 over 2, so I'm just going to be plotting a couple other slope points. And you guys are obviously going to be using a straight edge, so you're going to have a lot more points. They're going to be easier, especially when we have our straight edge. Now test the point 0, 0. If I plug in 0 for x and 0 for y, we get 0 is less than 2. That is true, so I'd be shading below this graph. Okay, so let's just keep that in mind. I'm going to make a little notation to myself. I'm shading below on that graph. Now plug in the next, now look at the next equation. Make x 0. Okay, if I make x 0, think of it as an equation. Yes, I realize it's an inequality, but think about it as an equation. Y is going to be a negative 2. If I make y 0, x is a positive 4. So I graph this equation. Positive 4, negative 2. Again, it looks like our slope is 1/2. Okay. Now let's see where we're shading here. Test your point. Plug in 0, 0. 0 minus 0, 0. 0 is going to be less than 4. That's true. So I'm shading in between those two lines. Okay, so let's keep that in mind. Now looking at our last one, we have x plus y greater than or equal to negative 2. X is 0, y is negative 2. If y is 0, x is negative 2. So that's an easy one. So I have negative 2, negative 2. Oh, that's kind of nice. It gives us some of our values. And now, remember, we're shading in between. We need to test a point. So if I plug in 0, 0, 0 is greater than negative 2. That's true. So this region's unbounded. Okay, I would have this whole region in there. Okay, so our test points. Our test point, one of them is negative 2, 0. And when I test that in this function, and I want you guys to be showing me negative 2, let me erase that. Okay. 2 times a negative 2 plus a 3 times a 0, that's going to be a negative 4. Now if I plugged in my other point, which is 0, 2, I meant to say negative. We have 2 times 0 plus a 3 times a negative 2. That's going to be a negative 6. Now to figure out whether these are maximums or minimums, because any one of these points that we've shaded is a possible answer, but we only have to test the vertices. Test another point that would be in the shaded region. So I'm going to test this point right here, which would be 7, 3. So I'm going to test the point 7, 3. The reason that I'm doing that is I'm testing to see, are these maximums or minimums? So when I plug in 7, 3, we get 2 times 7 plus a 3 times a 3. We get 23 there. This is a max. So any point that I plug in here that would be in this shaded region, even off my graph, would get me a maximum, would get me a bigger value than either one of these two. Okay, so that's why there is no max, because the values keep getting bigger and bigger and bigger when I would plug them into our objective function. So therefore, the only thing our function has is a min at -6. Okay? Okay, there are your lesson questions, and please make sure your summary is submitted on time.